All right, in part 2 of 2.8, we are going to look at compositions of functions. So the idea here is just we can substitute one function in for the variable of another function to create an entirely new function. Our notation for that looks like this. Okay, it almost looks like a little O, right? This is our notation for f of g of x. It can also be written like this, where we can see that I'm plugging the entire function g of x in place of x in f. Okay, so let's jump right into an example. Let's say we have f of x equals 2x squared minus 4x, and g of x equals x plus 3. So, again, the notation, this just means f of g of x, like this. So this means I'm going to take my entire function of g of x and plug that in place of x everywhere in f of x. So that's going to look like this. I'll have 2 times x plus 3 squared. I'm just replacing this x with g of x, with x plus 3, minus 4 times x plus 3. And then we want to simplify this as much as we can. So I would want to square this out. And remember, our shortcut for that is square the first, take 2 times the product of the 2. So the product of these would be 3x, and then 2 times 3x would be 6x, and then square the last. And again, if you don't remember that shortcut, you can always come off to the side and just write this as x plus 3 times x plus 3 and multiply it out. All right? Then we've got minus 4 times x plus 3. Then I'll do my distribution and combine like terms. So this will be 2x squared plus 12x plus 18 minus 4x minus 12 if I distribute that negative 4 through. And finally, we can combine 12x and negative 4x to get 8x, and 18 and negative 12 to get 6. Okay, so this would be the composition of these two functions, f of g of x. All right, let's try one more here. Let's do f of x. So same idea here, but now I'm plugging f of x into f wherever I see an x. So that would look something like this. So 2 times, and I'm just plugging 2x squared minus 4x in place of x. So 2x squared minus 4x, that's squared, minus 4 times f of x. So 2x squared minus 4x. Right? So again, I just replaced the x that was here with f of x. Same thing here. So let's multiply this out and simplify. So again, our shortcut, square the first. So 2x squared would be 4x to the fourth. Take 2 times the product of the 2. So the product of these would be negative 8x cubed. If I multiply that by 2, I would get negative 16x cubed. And then square the last. So negative 4x squared would be positive 16x squared. Then minus 4 times 2x squared minus 4x. Do my distribution. So I'll have 8x to the fourth minus 32x cubed plus 32x squared minus 8x squared plus 16x. And the only thing that I can combine here is my x squareds. So I will get 8x to the fourth minus 32x cubed plus 24x squared plus 16x. All right. Now, we can also evaluate compositions at certain points. So let's take a look at g of f of 0, right? And again, I think it's a little easier if we rewrite this like this, g of f of 0. Okay, so what this means is I'm plugging 0 into f, right? I'm plugging 0 into f, and then whatever value I get there, I want to take g of that. All right, so I'm actually going to color code this here. Let's make this purple. So I want to evaluate f of 0. So f of 0 is going to be 2 times 0 squared minus 4 times 0, which is going to be 0 minus 0. That's just going to be 0. So in this case, this is just going to be the same as g of 0 because we found that f of 0 was equal to 0. Now that's definitely not always going to work out to be the same value there. Okay, we need to first evaluate that inside portion and then evaluate g of 0. So all I'm going to do now is plug 0 into this function. So I'll have 0 plus 3, and that'll be 3. All right, so why don't you guys take a second and try the next example. All right, I went ahead and wrote my work out already here. So f of g of 3 means I want to evaluate g of 3 first, and then take that value and plug it into f. So g of 3 would just be 3 plus 3, which would be 6. So that means I'm plugging 6 into my f. And when we do that, I believe we get 48. All right, so let's take a look at this same idea from a graphical perspective. So again, this notation just means g of f of 4, right? So what this means is I want to evaluate f of 4. In this case, that means find it from the graph. So this means what is the y value where the x value is 4? Well, here is where the x value is 4. So on f of 4 is equal to 2. So this just means I'm evaluating g of 2. F of 4 is equal to 2. So g of 2 then, if I go to where x is 2, g is equal to 5. Okay, let's try another one. Let's do for x equals 4, but let's do f of g of 4 this time. So again, I want to find on the graph for x equals 4 what g is equal to. So for x equals 4, g is equal to 3. So that means I'm evaluating f of 3. Well, f of 3 is equal to 0 right here. Okay, I'm going to skip down and do this g of negative 2. So again, this just looks like this. So first, I want to evaluate g of negative 2. So if I come over here, at negative 2, g is equal to 1. So what this means is I now want to evaluate g of 1. I'm replacing g of negative 2 with 1. So if I go back to my graph, g of 1 is equal to 4. Okay, so why don't you guys try a second and try these last two here. All right, so f of g of 0 would be f of g of 0. So at 0, g is equal to 3. Well, we actually already evaluated f of 3, right? F of 3 was equal to 0. And then the last one, f of 4, well, at x equals 4, f is equal to 2. We already actually did that up here, so this means I'm evaluating f of 2. So f of 2 is negative 2. All right. So now let's talk about the domain of a composite function. All right. Now, the steps to finding the domain are first find the domain of the inside portion. Right. So let's just for notation's sake for this one, let's assume we're finding f of g of x. So the first thing we want to do is find the domain of g of x. Right. Then we want to plug g into f and then find the domain of that function. Okay? We can call that domain B. Now, the domain of the whole thing then, of the composition, is the intersection of A and B. Right? What that means is we want all values that are common to both of those domains that we just found. And we practiced that in part 1. Okay, but we didn't add the notation onto that. Right? This kind of looks like an N, right? This is our notation for the intersection of two sets, all right? So let's first find the domain here of G, right? Here we're evaluating, or we're finding the domain of f of g of x. So my inside portion is G. Let's first find the domain of G. So if we think back to domain restrictions, we said that really the only things that could cause the domain to not be all real numbers would be negative values under an even root or zeros in the denominator. So just for G, we want to say, well, the domain here would just be all values except the denominator can't be 0, right? So I would subtract the 1 over and we would say x cannot be negative 1. So the way that I would write that in interval notation, we said that would be starting at negative infinity, going up to negative 1, skip negative 1, and then pick back up with negative 1 and go up to infinity. Okay, so this was step 1. This is the domain of the inside portion. Okay, here I'll label it as step 1. Step 2 then, plug g into f and then find the domain of that function. So that would be, let's see, 2 over, and I'm replacing this x with 5x or 5 over x plus 1. Right? I'm actually plugging g of x in place of x. So that'll be 5 over x plus 1 minus 3, like that. So I want to find the domain of this now. Well, again, we just can't have zeros in the denominator. So I'm going to say, well, this whole denominator, which is 5 over x plus 1 minus 3, cannot equal 0. And then I want to solve. So I could add the 3 over. 5 over x plus 1 cannot equal 3. Then multiply the x plus 1 up. So I'll have 5 cannot equal, and I'll go ahead and do the distribution. So that would be 3x plus 3. Subtract the 3 over. 2 cannot equal 3x. And finally, divide by 3. And we get that x cannot be 2/3. So the domain here for step 2, write it. Okay, if we're only skipping 2/3, I would say, well, I'm going from negative infinity up to 2/3, skipping that, and then union that with 2/3 to infinity. So now I want the intersection of these two sets. Okay, the intersection is all the values that are the same in both of these. So I'm excluding two values. I'm excluding negative 1 and I'm excluding 2/3. So my final answer, right, the intersection of these two sets would look like this, going from negative infinity to negative 1. And I'm putting negative 1 first because that's the smaller of the two values that I'm skipping. We do need to make sure that we're going in order when we write these. So negative infinity to negative 1, union that with negative 1 to 2/3. skip that value, and then 2/3 to infinity. So the domain of f of g of x would be this. It's all real numbers except -1 and 2/3, right? Let's try one more example here, one with some square roots. So again, we want to do the same thing. We want to find the domain for f of g of x. Right now, I should point out, when we're doing practice problems, make sure you pay attention to what they're asking you to do. They could be asking you to find the domain for g of f, right, or f of g. So just make sure you're paying attention. So here we are doing f of g of x. So the first thing I want to do is find the domain of the inside portion. So the inside portion is g of x, right? So step one, find the domain of this. So for roots, we said whatever's on the inside has to be greater than or equal to 0. So I'm going to say 4 minus x has to be greater than or equal to 0. I can just add the x over. I'll get 4 is greater than or equal to x. And to make that look a little nicer, we can just flip the whole thing around and say x is less than or equal to 4. So that's the domain for g of x. And again, we can write that in interval notation. And if we want everything less than or equal to 4, that would be -infinity up to 4. And I would include 4 because we're saying it's less than or equal to. The second step is to plug my g into f, right? So what that means is we're saying, well, I'm going to have the square root of the square root of 4 minus x minus 2, like that. I just plugged this in place of x in f. Well, again, all we care about is what's on the inside being greater than or equal to 0. So I'm going to say the square root of 4 minus x then minus 2 has to be greater than or equal to 0. So I can add the 2 over. Get the square root of 4 minus x is greater than or equal to 2. And then I can square both sides. So I would have 4 minus x has to be greater than or equal to 4. Right? Subtract the 4 over, we would get negative x is greater than or equal to 0. Divide by -1, and remember, whenever we're dealing with inequalities, if I multiply or divide both sides by a negative value, we have to flip the inequality. So here we would get x is less than or equal to 0. So in interval notation, that would be -infinity up to 0, and we are including 0. So the final step is to find the intersection of these two intervals. All right? Now, we talked about in the last video that it may be helpful to actually draw this out. Okay, so let me draw out a couple of number lines here. So I'm saying that the first one is I'm starting at 4, and I want everything to the left of that. This one, I'm saying I'm starting at 0, and I want everything to the left of that. So the intersection, or in other words, the overlap of those two is actually starting at 0 and everything to the left. So the domain of the composition of f of g of x, in this case, would be -infinity to 0, including 0. Okay? The overlap between these two steps here, that's the domain. Right? The final idea for this video is just rewriting a function as a decomposition. Okay? So here we're saying this is my already composed function. write this as two different functions, f and g, such that h of x equals f of g of x. Okay, and there's more than one correct answer for a problem like this. Okay, but the idea here, okay, is to say, well, I can split this up into two functions. I could say, well, if I want to make f my larger function and then plug g into it, for this example, I could say something like f of x equals 1 over the square root of x, and then my g of x is whatever's on the inside of that square root, 2x squared plus 1. Right? So if we think about then composing these two functions, f of g of x, so if I take this and plug it in for x here, I would get exactly what I want. I would get 1 over the square root of 2x squared plus 1. All right, let me give you an example of another correct answer for a problem like this. I could say something like f of x equals just 1 over x, and then my g of x would be the square root of 2x squared plus 1. Okay, if I were to compose this and plug this entire function in place of x here, I would also get exactly what I wanted. Right? So there's more than one correct answer. Right? So since there is more than one correct answer for problems like this, I want you to just pause the video and try this one. I'm not going to have it pop up on the screen, but pause the video and try this one for a second. All right, so we could do, again, this a couple of different ways. Right? I could say that f of x is x to the fourth, and g of x equals x squared plus 5. Right? So I would be plugging this in place of x to create this function. We could say this would be a little bit less common, but we could do something like f of x equals x squared, and then g of x equals x squared plus 5 squared. Right? I mean, again, this one probably it wouldn't be your first thought, but this would still definitely work. Right? So there's more than one correct answer for these types of problems. All right, that is it for this video. The final question is going to pop up asking you what questions you have.